Hi, I'm Meli.
Hey, I'm Krishna Kumar. You can call me KK. We are here today to walk you through a presentation on PostgreSQL physical replication, the internals of this, recent developments, and what sort of future work can be done around physical replication.
Hi again, I'm Meli. I'm working at Microsoft as a software engineer. So, my current team is the open source Postgres team, where I and rest of my team are working to contribute the open source Postgres. Uh, so, I spent the last 2 years working on mostly replication. Started with logical replication, then in the past year, I'm more focused on the physical replication, trying to learn how it works. So far, I also like given talks about my experiences, how I got started with Postgres and how to contribute it. And yeah, previously again at Microsoft I worked on different teams, but they were all again with Postgres. So I did some work for Azure Database for PostgreSQL, and I worked with Citus team in the past. So yeah, that's little like a brief introduction of myself.
Cool. I'm KK. I'm engineering manager for Postgres open source contributors and Postgres engine team. Started with Linux porting to new boards and device drivers. Worked in a company called NatureSoft for a while, moved to HP, did more high performance computing style stuff, and worked on a startup of hybrid cloud storage called StoreSimple, which got acquired by Microsoft and then came to Microsoft. The most exciting part of my job nowadays is interacting with PostgreSQL folks, the top folks in who contribute the like a large amount of like features into PostgreSQL as part of our committers and contributors team. Uh, Today we are bringing you some of the learnings from those interactions as well as our own experiences with physical replication, and let's get going. So from a start point of view, let's just talk a bit of terminology. So the first thing which kind of confuses everybody is what's the difference between physical replication and logical replication. And it took me a while to get it when I was beginning with PostgreSQL, but just to give a quick overview, Postgres deals with everything in terms of WAL records, in the sense that whenever there is a change made into the database, that will end up with either like a single WAL record, like a multiple set of WAL records that are there. In case of physical replication, these WAL records is what gets transmitted between, let's say, a primary primary Postgres instance and a standby Postgres instance. Between them, these WAL records get transmitted, and primary, whenever changes go into primary, the WAL records get to standby, and in standby also these changes are made as well. So that's the high level view of the physical replication side of things. Then comes the logical replication, where it's actually the SQL statement itself which is like converted and like communicated and replicated, which is like quite different from the physical replication case where WAL records are directly communicated. Now, in both physical replication as well as logical replication, the presence of endpoints, as in like we have a primary, we have standby one, and maybe we have a read replica, like which is also consuming this primary's data. All of them are represented in terms of slots. So for physical replication, logical replication, there will be slots, which is the concept where in the software of Postgres, it's equivalent to there is another endpoint which is replicating from this source that is there. So that's the slot concept, a representation of the endpoints. The other few other few terms which we'll quickly go through is like what is synchronous replication and what is asynchronous replication. In terms of synchronous replication, think of this as if you have a transaction come into the primary, until it gets reflected on the standby or the set of standbys that is chosen for the quorum, then until then the transaction is not considered successful. So as you can imagine, this is a feature, right? Like where synchronous replication can be used for something like high availability, where there's a primary and a standby. And when the standby has some issues and it goes down, when the primary has some issues and it goes down, the standby can really pick it up. So that's one place where synchronous replication gets used. There are many other places where this gets used as well. But because synchronous replication does not have the challenges that the data is not like lost every time you are committing on the primary, it's also guaranteed that standby will have it. Because of this, we can use it for a scenario like HA. Coming to something like asynchronous replication, where there is no guarantee that when you commit locally, it is also committed in the remote scenario, where like when primary commits a transaction, doesn't mean standby is already caught up with it. It will eventually catch up depending on the performance of the network and a lot of other like factors coming to picture. But these scenarios can be used in cases like, let's say, read replica, where you are not really looking for exact data to be available, and you can wait for the data to come in. But at the same time, you do want to have the communication between the primary and standby, and making sure that whatever goes into primary eventually ends up in the standby as well. And you can run queries which will be analytical and other sort of queries. So that's where one scenario where asynchronous replication can be used as well. GRDR, and there's a bunch of these scenarios where it gets used, but conceptually, synchronous means that we have persisted and made sure that primary and standby are in sync, and then async means it can take time as well. Quickly, we will talk a bit on the streaming part of this. So when it comes to physical replication, you can actually have other scenarios where you copy the vault records onto the standby and make the standby recover from those vault records. But in case of streaming replication, there is a full-on connection between the primary and standby, and the vaults are streamed from primary to standby. So it is a consistent connection that goes on, and we'll go into details of that in the presentation. In the context of this talk, we will be talking about physical replication and synchronous and streaming replication in pictures. So physical streaming, synchronous replication is what we will primarily focus on. So here is just a setup. So we'll go into the details of how this works, but primarily we will just quickly look at what is there when we try to do some of these physical replication setups. So here is in the screenshot, what we show is primary on the top, like it is output from the primary PSQL connection, and the bottom we have standby logs. So you will see the arrow which points to the points from the top to the logs. That indicates that primary is at a certain LSN number, like the DA0 number. That is what is currently there on the standby as well, right? Like all of the LSNs like sending, flush, and apply are all consistent, and it is there in the primary as the current LSN that is being operated on. When we do an operation like create table, that's what is shown in the next set of operations. So when a create table happens, obviously the LSN moves forward in the primary. But when you look at the logs, what you can see initially is that the logs start with the LSNs not fully caught up, but eventually by the time the table transaction goes to the standby, you will start to see the LSN match there as well, which is the new LSN which has been created, the vault record which has been created on the primary. So this is a demonstration of how the physical replication setup happens, and like how they can come. You can look at the logs and kind of see what kind of movements happen with respect to LSN. So that's basically the intro and the logging comparison that we have. Let's move to the next. Go ahead, Miss.
So yeah, thanks, KK. So let's dive deeper into how physical replication on Postgres works. So this is a simple overview of components that make the physical replication happen. So you see that like the flow kind of is from left to right, and it starts with your application, and application connects to the Postgres backend process. So at this point, like KK mentioned, the replication heavily relies on WAL files, like WAL data, so that like there are many different processes in Postgres that can generate WALs, and the user backend process is one of those, and there are WAL writer and checkpointer. All of those can write WAL into WAL buffers, and eventually those WAL data from in the buffers needs to be flushed to WAL files, like to the disk as WAL files or WAL segments, to ensure reliability in the cluster. And when you set up the replication, there are like two important processes. One is WAL sender, the other is the WAL receiver. WAL sender is on primary, that is responsible for sending WAL data from primary to standby. And on the standby side, the WAL receiver is the one that communicates with the primary, and it just receives WAL data from primary and then writes into standby's disk. So let's move on with how this WAL generation works first. So this is our primary setup. We have like application already connected to Postgres, and like we have buffered some files ready there. So first thing, as a user, I start my transaction by running begin, and like begin command just inserts a WAL record into WAL buffers. So it basically generates a WAL data, and in this case, its LSN is 0. So you can see that the WAL buffer has an LSN 0 record, and you can also see that there's already a WAL 0 file from before. And then I move on with my transaction and just keep running some more statements. And like since I keep running the query, Postgres keeps inserting the WAL records into WAL buffers. You can see we have now LSM 1, but still we don't have any new WAL files yet. So eventually I will run commit to end transaction, and the commit itself also will insert a WAL record, the LSN2 here, and just before transaction ends, the commit statement also triggers Postgres to flush WAL buffers from WAL records, like WAL data from WAL buffers to WAL files to make them persisted on disk. So you can see that after running commit, we now have a new additional WAL file, WAL1 in this case. So this is how running a query can generate a WAL file on your server. And when we move to the replication side, now standby server comes into picture here. So again, initially we have all the processes we need, and we started the replication, and like initially standby tries to connect to primary, so it sends a connection request, and when the Postgres backend receives that connection request, it will immediately launch a WAL sender process. Until a standby tries to connect to primary, there will be no WAL sender process on your server. But when the standby is there, WAL sender should be there too, so it will launch the process. And then standby will start communicate with the WAL sender by its own WAL receiver process. So WAL receiver will send its standby's latest LSN to primary, so that WAL sender can decide, which wall data should be sent to standby. So after getting the LSN, what wall sender will do is simply reading wall from disk. It will just read necessary wall data and will try to send to standby. And on the standby side, wall receiver is the one who is receiving this incoming wall data. And after getting the data, the wall receiver will directly write wall data into disk as wall files without attempting to write anything into wall buffers. And eventually, since this wall data on standby needs to be applied to make standby and primary in sync, at this point you see that we now have missing wall files on standby right now, wall 0 and wall 1. So the startup process is the one that reads these wall files and simply just applies those wall data to apply those changes into standby server as well, so that the primary and standby will be in sync. So this was like how replication works in a nutshell, but like it's a feature that keeps improving with every release. So I just want to mention some few recent works about replication. First one is the reading wall directly from wall buffers. This feature will hopefully come with PG17, and it will. So as you remember, I just mentioned that the wall sender reads wall data from directly disk without looking into wall buffers. This feature makes wall sender to look into wall buffers first, and then if data does not exist there, then it can look into disk. So, and the next things, of course, like there are many bug fixes. Like one of the interesting bug fixes that fixed in version 16 was standby servers. Like startup process on a standby server was crashing. It's by saying cannot allocate any memory when the primary server is not available. So this is one of those bugs that fixed in the last couple releases, for example. And the last thing is this, like allowing the wall processing to prefetch data beforehand. So this is actually is there since the version 15. So it's a feature that prefetches wall data before you actually need those data. So like Postgres can somehow know or predict that you will need those wall data at some point. So it prefetches beforehand so that when you need those data, it will be faster to read and use those walls.
So coming to the opportunities that lay in front of us, right? Like, so as Nelly was explaining, physical replication is an evolving area. A lot of work has gone in till now, but a lot of work remains in front of us as well. And here are a few things that we have picked up from the community, from discussions that we have had and things like that. And the idea is that these opportunities provide inspiration to folks who want to work on physical replication, as well as come together and contribute and make Postgres even go to higher heights than it's already there. So here specifically, as Melly was saying, on the primary, we do have in PG17 a feature which will make sure that we are no longer going to the wall files to read when the walls are sent across. But if you go back to the slides that we had in the beginning, where we talk about the standby, how it persists the wall record after getting from the primary, there is a place where we could do the similar thing on the standby as well. And that's one area which could use some contributions where we read directly from the wall buffer. and then thereby avoid file operations when on the hot path that is there. The second part of this is that every time, the second item that we would like to talk about is that like every time we have to send a wall record, we also have to wait till the wall is flushed in the primary. Until that is done, we don't send it to the standby. This is done for primarily because of correctness and consistency perspective. But if we get to a place where we can modify the communication between primary and standby to send the wall even before it is fully flushed, but the standby does not apply these walls, but does all the pre-processing required before the wall is applied, like maybe checksum checks and other things are already done and it's just waiting to apply. This can introduce scenarios where specifically, let's say cloud network disk kind of thing. Nowadays, like there's no like direct disk in most cases. It is all managed disk that gets used where there is some sort of network in between. And this serialization currently prevents us from capitalizing the scenarios where we can parallelly send it across the network, like via the disk drivers and things like that. But like don't wait for the local flush to happen. So if we have a feature where this is decoupled, the serialization is decoupled, and we have some sort of protocol modification, then we will improve a lot on the latencies that we have with respect to physical replication. The other part of this is that right now when on standby, we are doing the wall flushes, and then we are prefetching these walls and applying in the standby. Whereas if we really just do the wall writes and then indicate that we are almost ready, but don't apply, we will again like be able to do the pre-processing parts of these operations, thereby improving some of the resource usage on the standby and performance. Other idea is that right now the communication between the primary and standby is typical network communication. In Linux, we have this IOU ring functionality which has come in. It's revolutionized a lot of networking and storage, operations. So could we bring IOU ring into the networking area in Postgres and thereby evolve to a place where the communication channel between the primary and the standby takes benefit of this? So that's another thought that we have, which we want to put out to invite more collaboration and contributions. So that's those are those opportunities. Thank you for listening in to the talk. As is the case with any talk, there's a lot of people supporting this talk to make the final thing happening. We'd like to thank the Microsoft committers and contributors team. Special thanks to Thomas and Anders, because a lot of this has come from offline discussions with them. But all of the team has contributed to these. Thank you for PostGres organizing community, as well as PostgreSQL community for all the great work on which we are all greatly standing on the shoulders. Thank you.
Yeah. Thanks, everyone.